Okay, question 5. We've got a rectangular distribution question. We're given one about the rounding error. So we've got the strength of a pongal measured to the nearest tenth of a millivolk. And given that the rounding error has a rectangular distribution, we have to explain why the probability density function is 10 between plus and minus 0.05. So, first things first, we need to say that we know that the minimum and maximum error of a rounding error to 0.1 is plus or minus 0.05. So the upper and lower limits of the distribution are 0.05 and minus 0.05 because these are the maximum and minimum of the rounding error. And now we need to explain why the value of the rectangular distribution is 10, and we can either do it by looking at the area of the distribution, or we can do it by using the definition of the distribution. I'm going to do the latter. So if we just turn to page 11 of the formula book, we've got this section halfway down the page about continuous distributions, and we're told here that a rectangular distribution has got a probability density function of 1 over b minus a, where b and a are the upper and lower values of the distribution. So we can use that, so we can say so f of x equals 1 over b minus a, where this and this are a and b, which is 1 over 0.05 minus 0.05, and that's 1 over 0.1 equals 10. Part B asks us to write down the mean of x. Well, I'm just going to draw the probability distribution. I'm just going to draw it up here. I've got a little space. So the probability distribution goes up to 10 from minus 0.05 to plus 0.05. And we know that the probability distribution is symmetrical, and therefore the mean is in the middle. Well, they're either side of 0, so the mean is 0. Good. Part C asks us to prove by using integration that the standard deviation of x is 1 over 20 root 3. Now, if we again look at the formula book, we can see that the standard distributions, the uniform distribution, we're given the variance, a 12th of b minus a squared, but the question is asking us to prove it, so we can't use this result. This is what we're actually going to prove. So instead we're going to use this here, the variance, and we're going to use this formula that the variance is the integral of x squared times f of x minus mu squared, and we're going to prove it. So the variance, we'll start by finding the variance and then we'll find the standard deviation. So the variance is the integral of x squared f of x dx minus the mean squared. Well, we know the mean's 0, so we can ignore that. So we've got the integral of x squared times f of x. Well, f of x is 10, so it's just 10x squared. And we have to put the limits of integration in, and these are the values of b and a, so it's between 0.05 and minus 0.05. And like I say, we can forget about the mean because that was equal to 0. So integrate this, add 1 to the power, divide by the new power, so we get 10 over 3 times x cubed between. Now I know what's coming, which is that we're going to square root this, and you can see it's in fractions and surds, so having it in decimals is not much good, so I'm just going to convert these to fractions. So we've got between plus and minus 1/20th. And I'm just going to take that 10 over 3 outside as well. I think that's going to just make life a bit easier. So we're going to do a 20th cubed, and a 20th cubed is 1 over 20 cubed, minus a 20th cubed. And when we cube a negative number, we get a negative number. So we're going to get 10 over 3. Now you can just do this on your calculator if you want, but I know what 20 cubed is. It's 8,000. So it's 1 over 8,000. Minus minus is plus 1 over 8,000. So we get 10 over 3 times 2 over 8,000. And again, if you want to do that on your calculator, you can. I might just do that. We've got 10 divided by 3 multiplied by 2 divided by 8,000, and I can convert that to a fraction, and we get 1 over 12,000. 1 over 12,000. And this is the variance of x. So the standard deviation is the square root of that. And I have been asked to prove it, so I am just going to show how to do this. So 12,000 okay, so it's actually not 12,000. I think I made a little mistake there. I'm just going to do that calculation again because I think it's 1 over 1,200. So on my calculator we've got 10 over 3 multiplied by 2 over 8,000, and if I convert that to a fraction I get 1 over 1,200. So here it's 1 over 1,200. So converting that to an exact surd, 1,200 is 100 times 12, so we've got the square root of 100 times the square root of 12, and the square root of 12 is the square root of 4 times the square root of 3. So putting all that together we get 1 over 10 times 2, which is 20, square root of 3. And that's quite a tough question, but it has come up once or twice, so it's worth making sure that you can do that. Distribution of a rounding error and a proof of a standard deviation. Okay, and the last part shouldn't be too bad. Find the probability that the absolute value of x is greater than sigma, the standard deviation. I'm just going to put this on my diagram. So we've got a value x, and we're asked to find that its absolute value, so that means irrespective of whether it's negative, is greater than the standard deviation, where the standard deviation is here. So the shaded region that I've shown on the diagram is the area that we want, whether the absolute value, irrespective of whether it's negative or positive, is bigger than standard deviation. And we can see from the diagram, we know that the standard deviation is 1 over 20 root 3. So we want, the area we want is 1 minus this region here. So if I work out this region and take it from that, so we get 1 minus, well, the distance from standard deviation to 0 is 20 root 3, so the distance from here to here is 2 lots of 20 root 3, and so the area of this rectangle is 10 times 2 lots of 1 over 20 root 3. So that's 10 times 2 is 20, the 20's cancelled, so we get 1 minus 1 over root 3. And I might just do that again on the calculator. So 1 minus 1 divided by the square root of 3. Hit enter, and we get 3 minus root 3 divided by 3. I think I'm going to put that as a decimal. So we get 0.4226, so 0.423 to 3 decimal places. And that is question 5 finished.